Good afternoon, dear students. In this series of named reactions, today we will be dealing with Wittig reaction, which was published by George Wittig in the year 1954 after his extensive work on this. And for this, seeing the utility of this reaction, the regiospecificity of this reaction, how it is applied in varied processes, he was awarded the Nobel Prize in the year 1979. For this, I have also read a few references. One of them I have put up here if you want to consult, which was published in Journal of American Chemical Society in the year 1998. It deals with these stereochemical aspects and the stereochemistry in a very vast way. So I have taken up a few points from there. Now, talking about Wittig reaction, as to how this Wittig reaction proceeds, is basically this is a 2+2 cycloaddition reaction. 2+2 cycloaddition reaction implying that a carbonyl C double bond O reacts with a phosphonium halide, which is again phosphorus, which bears a phosphorus, and there's a double bond between the phosphorus and the carbon after a halide has been formed. So this type of a reaction, and how it occurs is the aldehyde, it reacts because the carbene ion is formed. So the aldehyde, it reacts in this way that the carbon of the carbonyl is positive, electromeric shift. As a consequence, the C negative between this, because this is triphenyl phosphine, so this double bond, this will be shared with this P positive, hence a 2+2. So because this has been generated, a negative charge here, so the name halide, a negative and a positive on adjacent carbon, implying this is called as a halide. So this reacts. So as a consequence of this, carbon negative attacks the carbon positive, a nucleophilic addition takes place, and because of that, PH3P, now with the oxygen negative, it leaves, and we get a double bond, the position of the double bond being very clear because it is located where? Between the carbonyl carbon and where the oxygen was. In place of that oxygen, what will be formed? In place of that, the CH will be attached, the carbene ion. So the position of this bond is very clear. Hence, this is a regiospecific reaction, because that's why it's so important, because otherwise preparing alkenes is a problem. They tend to rearrange, and the double bond can be positioned in a number of ways depending on the substitution and the reaction. Hence, we get multiple products. In this case, it is regiospecific, so the position of the bond is specified that it is present between this and the carbon, which bears the negative charge in the halide between these two. Now, how does one prepare a halide? Preparing a halide, one takes a primary alkyl halide. This primary alkyl halide reacts with this triphenyl phosphorus. This is an SN2 reaction because the electrons which are present here on this carbon, on this phosphorus, these are shared by the carbon. Why are they pulled towards the carbon? Because the Br tends to leave as Br negative. This is pulling the electrons towards itself. As a result of this, this bond becomes weak, and an SN2 substitution takes place in one step. So in one step, this attaches here. As a result of this, the phosphorus will tend to get a positive charge because it's given a lone pair of electrons here, and the bromide will therefore leave as Br negative. So this phosphorus gets a positive charge. Now, when a base is added to it, in the presence of a base, because phosphorus has a positive charge, so it will be attracting the electron from the alpha carbon towards itself. As a result of this, this hydrogen, alpha hydrogen, becomes acidic. In the presence of a base, this will be pulled away as H positive, leaving the electron pair to form a double bond with phosphorus. So in the presence of a base, we will get, now this carbene ion in other words has been generated. A carbene ion has been generated, which when pulled towards the phosphorus will form a double bond. So this is a halide. This is a halide. Halide implying phosphorus positive and carbon negative. Two opposite charges on adjacent atoms. So this will then be pulled, this carbon negative, the electron pair towards phosphorus, so that its valency is complete. So this is phosphorus halide. Now once this phosphorus halide has been formed, this in itself is very reactive. So what will happen, because this will then react with our carbonyl, which can be an aldehyde, or it can be either aldehyde or it can be a ketone, either of them. Here a ketone has been shown, so it can be either of the two, either an aldehyde or a ketone. And as we can see, as the mechanism proceeds, because carbon will be carbon positive, the halide carbon, now here this will be having a negative charge, because this has been shared, the electrons are shared here. So this P, the carbon double bond P, this electron pair will be attracted towards the carbon positive of the carbonyl. As a result of this, a bond will be formed between the positive carbonyl carbon and the negative anion of the halide, carbon negative. So a bond is formed between the two, and since the double bond now between phosphorus and carbon breaks, this electron pair is now with a carbon positive forming this bond. So again phosphorus will get a positive charge, and oxygen, of course the carbonyl oxygen, getting a negative charge. Now in this case, this is R3, R4. It can also be the other way around. That is because it is the attack can take place so that rather than having R4 on this side, the left hand side, and R3 on the right hand side, one can also have the R4 on this side, that is this right hand side, and R3 on the left hand side. So it can be either way. Similarly, when these, now the positive and the negative will tend to form a bond. As a result of this, we will be getting this oxyphosphatane, that is PH3P with O negative forming a bond. So this type of a structure is formed, which is known as the oxyphosphatane. This is the one which is participating in the reaction. So as a result of this, what will happen is that this four-membered state will be formed. And this four-membered state, when they'll collapse to give us this product, because P positive will be pulling here P and oxygen. So between P positive and O negative, this bond has been formed. Now what will happen? Because phosphorus will tend to form a double bond with this. So as a result, this oxygen will be continuously pulling electrons. So P positive with P, now with double bond oxygen. And at the same time, this bond will be, this will be forming a double bond here. So we will tend to get PH3, P double bond O, and an alkene. Now this alkene that is formed, as is shown in the structures above, that it can be that R2 and R4. It can be either way. See that R2 and R4 are opposite, or we can say R2 and R3. They are on the same side in one, because if this structure from the oxyphosphatane is formed from this structure, and on the other hand, if the oxyphosphatane is formed from this structure, then in that case what will happen? In that case, the R2 and R4 will be on the same side. Here R2 and R3, they are on the same side. In other words, we can get from this a mixture of, when it collapses, either assist, depending upon what these R1, R2, R3 and R4 are, we can get either E or Z, cis or trans. That's why this has been shown by Wrigley lines, because now this outcome, the stereochemistry, will depend on the type of halide we have selected. Though generally in a common reaction where the Z isomer is the main product and E is the minor product, in that case R is equal to alkyl, the general unstabilized halides which are selected. In that case, we will soon see as to how this happens, that we are getting Z as the major, and it's a mixture, but Z is the major and E is the minor compound that is formed in this reaction. Now, where we are using unstabilized halides, in that case, that means where R is equal to alkyl. In the halide, that is PH3CHR, that R, PH3PCHR, that R is equal to an alkyl group, that is known as an unstabilized halide, because R is not stable to make this halide stable, because C is negative. C negative and R has a plus I effect. So it is called as an unstable halide. This type of a halide is an unstable halide where PH3, C will be the anion, that is C negative, HR, and this R will increase this negative charge further. Hence it is called an unstable halide. And now when this state I have shown here is the transition state. And how is this transition state formed? Because then when PH3PCHR, this reacts with the carbonyl, then it will tend to form this type of a transition state. And this seems rather weird, but it is not. See, it's like a six-membered state, but which is folded. Why? Because this is called a puckered state. Puckered means that it is folded so that maximum eclipsing transitions, that is maximum interactions which are crowding, they disappear. We will see as to how PH3P. Now this is the O of RCHO. Why has it come here? Because O is trying to form a bond O negative with P positive. P is positive. Here, this is the C negative of the halide. Now, this C negative is trying to form a bond with this RCHO, the C positive of this carbonyl. So, as a result of this, what will happen? This folded type of a structure will be formed. This folded structure, we can see over here that this R and this R, they are quite far away. Otherwise, had they been close, as we'll see in the other structure, then they would have caused a steric crowding. So they are away from each other. When this type of a structure, because this is the transition state, the puckered state. So when this type of a structure is formed, this will then collapse and we will get the product, as we can see, H and H here, H and H. They are on the same side. And at the same time, R and R, same plane, same side. R and H are on opposite side. But H and H are on the same side. Similarly, R and R dash are on the same side. So when this collapses, we will tend to get this type of the P positive with O negative. The transition state will form this oxophosphatine. This is the intermediate, and this will then collapse to give us, because the double bond, oxygen negative will leave, phosphorus will leave this electron pair here. So we will get a double bond which will be located where? In between these two carbons. So the location is clear, and moreover we will be getting a Z product, cis, because we saw in the transition state the cis was the favored product in this. As crowding was minimized, so it is similar to like what happens in the case of cyclohexane. Of course that it is not like the cyclohexane, but similar folding occurs here. That's why I mentioned like in the six-membered transition state, in the six-membered cyclic structure. So similarly we have a structure over here which resembles that. It is not cyclohexane, but it resembles that structure in puckering. like the boat and the chair forms there, and the skew boat. So similar type of a structure is formed by virtue of this attack. Now let us see if this happens in an otherwise manner. That is, the reaction is the same. That is, when the halide is reacting with, again, this is an aldehyde in this case, RCHO. Now we can also form this type of a puckering, can also occur, folded structure. That is where the PH3, we can see PH3, PCHR, it is here. But in this case, now in the earlier case, the R was where? The R was in the upper direction in the earlier structure. Here, the R is below. It can be either way because it can be folded, directed upwards or downwards. When this attacks, when this type of a transition state is formed, that R being downwards rather than being upwards, so what will happen? As we can see, in this also PH3PO. O from where? From R-CHO. And this is PH3PCHR. So we just have to place it right. This is PH3PCHR and this is R-CHO. This puckered means folded structure. It is folding itself. But this is the other way. It can be folded. But in this case, as you can see, there will be this 1, 2, these interaction which will tend to be crowded. R and R dash are close together in this. So these are destabilizing interactions. Moreover, in this case, even this R and this pH, as we can see, the phenyl ring, they are also on the same side. This R and this are also on the same side. So with the result, what will happen? Due to these interactions, this structure will not be all that stable because the crowding is more, destabilizing interactions are more in this case. And when this forms an oxyphosphatane, in that case what will happen? In that case we will get this type of a ring where PH3PO, and as we can see here in this transition state, that here where R is going downwards, whereas this R dash is going upwards. That means they are trans to each other, which is made more clear by the H's. This H is upwards. Over there the R was here and the H was here. That means, in other words, they were trans. But here, but the R and R was cis over there and the H and H was cis. Here, the H and H are trans, implying that this and this are also trans to each other. This is like pseudo-equatorial and pseudo-axial. That's why I compared it with cyclohexane. I didn't mean it that way, that like it was cyclohexane, but like, similar to that, like in the cyclohexane ring. So H and H are trans, so automatically it implies that R and R dash are also trans to each other. So in this case, this will be the structure which will be formed, and when this PH3P double bond O is pulled, oxygen leaves away and an alkene is generated. As we can see, the alkene which will be formed will be the trans form because R and R dash are on opposite sides, as could be seen also by its transition state. So this is the reason why this form, or the we can say the E form, E alkene is the less stable alkene, whereas in the case of unstabilized halides, the Z alkene, as we saw, because it has less of crowding interactions in the puckered state, the folded transition state, it is more stable. Now from here, moving on to the other aspect, that is when our halide is a stabilized halide. Now what do we mean by a stabilized halide? Stabilized halide implies that this carbon which is bearing the negative charge, because halide is formed when in the presence of a base and H positive leaves, so this negative charge is generated here, which will form a double bond with P positive. So this negative charge, as we can see, it is stabilized by this RCO. See, an ester or something like this is present which can stabilize over here. Multiple bond as such, which is electron pulling. And because it is electron pulling, RCO, this will tend to stabilize this negative charge. So that is the only reason, no other reason why this halide is known as a stabilized. Now since this is a stabilized halide, the unstabilized one reacted very quickly. So, there was kinetic control because it's unstable. So, it will act in haste. Act in haste means that the reaction will be too quick. So, because it will be so quick, and we saw the interactions also, the Z will be the preferred form. In this case, where this is a stabilized halide, there the interaction will tend to form in such a way so that there is thermodynamic control. Due to this thermodynamic control, what will happen, that as this oxyphosphatine is formed, during that formation, it will be in such a way so that the more stable intermediate is formed. The more stable, implying that this is away, the RCO is away rather than being towards this R dash, it will be away. In that case, they were on the same side. In the case of unstable. In this case, they will be what? Away from each other, because that was the kinetic aspect. This is the thermodynamic aspect. So they are away from each other. As a result of that, as we can see, when this type of an intermediate oxyphosphatane will collapse, this will then tend to form the E alkene as the major product. So what did we learn from this? That unstabilized halides, by virtue of the puckered crowded state, transition state, in case of the formation of E, do not tend to form E. Therefore, because the crowding is less in the puckered state, where the Z is being formed in that transition state. So Z is the major product because it's a kinetic control. Here the control is thermodynamic consideration. So as a result of this, otherwise had the other thing occurred, that is, in other words, this type of an oxyphosphatane had been formed, then in this case, see, the COR, that is this end, and this R dash, they will tend to interact. So these will be less stable. So Z will not be preferred. What will be preferred, in fact? In other words, the E state will be preferred with our stabilized. So the unstable halides, they were giving one form, whereas the stabilized, as we saw, they gave rise to the E alkene or the E form or the trans form. Now let's move on to Schlosser modification in the same reaction. Schlosser modification is nothing but that when we do this, the Wittig reaction is done in the presence of, he gave this modification because he observed when this was done in the presence of a lithium salt, then what happened was whether we used stabilized halides or unstable, that is whether R was an alkyl or R was a group which was showing minus effect like an ester, etc. In both the cases, we got, by this modification, a transform. How was this possible? This was possible because in the presence of this lithium, this ring opening occurs of this phosphorine ring opens up because O negative is stabilized by Li positive. And when this opens up, we will know this P will get a positive charge. Now this phosphorus is getting a positive charge. So when phenyl lithium is added to it and an H positive is removed, in that case now what happens is that we are getting a new halide is being generated. A new halide. Now this new halide which is being generated can therefore, because it is now single bonds, carbon, single bond carbon. So whether it is Z also, it will just change to the more stable transform. So it will change to the more stable. Here, even if they are on the same side, H and H behind each other, R and R behind each other, in that case, that is, they are on the same side. In that case, what will happen? In that case, due to carbon single bond carbon rotation, what we have now is the other distereoisomer. So we can say that now R and R dash, they will be, as can be seen, due to carbon single bond carbon rotation, when HX is added here, so this will change. O negative will change to OH. As a result of that, this O negative will change to OH, and as a result of that, after that pH P, this pH P O negative, this will be eliminated, a double bond will be formed, and this time when a double bond is formed, R and R dash, they are present on the opposite side. That is, no matter what, whether the halide is stabilized or not stabilized, in both the cases, in the presence of a salt, we will get an E form. So if we require a Z form, one should be using, besides the fact that the R is equal to an alkyl, that is, it's not stabilized, that it should be devoid of salt, that it should be salt free. Then we will get Z, otherwise we will get E always, whether the halide is stabilized or not stabilized in both the cases. Now let us see one problem pertaining to this, which is an interesting problem, where the problem is such that this is made to react with triphenylphosphine. It is Wittig type of reaction, and this then further reacts with this salicylaldehyde. So what will be the product? So let's see what happens. PH3P in the first step will tend to form, this will give its electron pair, so Br negative will be eliminated as an SN2 reaction, like it happens for halide formation. And when this will be formed, so this PPH3, now P will get phosphorus will get a positive charge, Br is left, SN2 reaction, because now P has given the lone pair of electrons. This in the presence of a base, what will happen? The base will tend to withdraw H positive from here. So electron H positive leaving its electron, and by virtue of this, because this electron has pair is here, so therefore Br will therefore leave as Br negative. When it leaves as Br negative, we will be getting this double bonded, a double bond will be formed here, double bond formed here as can be seen, double bond is formed here, Br leaves, so we will get this as the product. Now this is like a halide, not exact. Now what will happen when this is further reacting with salicylaldehyde? See, P is positive. So what will happen with P positive? P positive is able to, and P positive, and at the same, it will be attracting the electron pair towards itself. So as this electron pair will be, because we know this will become, so that it becomes double bonded here, and this positive charge disappears. But what will happen to this end then, this terminal end? So what the OH will give its lone pair at this end as this double bond moves towards the phosphorus. So as a result of this, the type of bonding that will occur, because OH here, and so it has become OH, H is left as H positive, so O, now C, H here, C here, C over here, the CH2 which was there. If you remember, this was earlier a double bond. This was a double bond earlier, this one. So now this has become a single bond because oxygen is given the lone pair here, and the double bond is shifted here. After this, this will tend to form, because oxygen will be O negative, and this is P phosphorus. If this bond moves from here, because this is O negative, this bond moves here, so this will move over here with this carbon, and as a result of this, a cyclic ring will be formed. Prior to this, we can show this in the form of this type of a structure, which is, if you know, this is more or less now, this is a halide, and this will then react in which way, so that this ring closure will occur, and we will get this as the product. First of all, this ring closure will occur, so PH3PO, and because this was a double bond over here, this shifted here from the phosphorus, while the oxygen which was attached here, the bond drifted from there to here, so PH3PO, and at the same time the product, this was the product that has been formed. So this is a very interesting reaction showing that how one can use this for the formation, because earlier see what was taken, a dihalide, triphenylphosphine, and in the presence of this benzaldehyde. So first of all an SN2 reaction which led to this type of a halide. This halide then reacted with benzaldehyde to form this cyclic structure oxophosphate. Oxophosphate then lost a P double bond O, P from one place, O from the other, and by virtue of that a double bond was generated in this cyclic structure. So that is all for today.